at 10:40, but we can talk. When we say that there is a torque that is being applied, right? So subsequently, there is one way that I'm applying a torque, but the object is not moving because I've held it. But if I'm applying torque, there is another case in which the object can rotate. So this whole thing in which you have a certain power that is given by the motor. So motor is technically providing horsepower or what are the units? Horsepower or kilowatt. We are using this so much. We are using so much that. So that power will subsequently give an RPM to the shaft. That power is giving a torque to the shaft. The torque is giving an RPM to the shaft. Salam. And yeah, so yes, you can also pick both of these pages. Okay. Yeah, so what I was saying was power, the motor will give power. Power means motor is giving torque. Torque given to the shaft means will translate into omega. So at the end of the day, your shaft is rotating, it has got some torque, and that's why you can calculate these shear stress concepts. That's why I specifically brought, because I keep on making those shaft and on top of them, those pulleys, right? But that's why I specifically brought this, so you have a clear idea that this is a very physical problem. In fact, we can also have a look at this one as well. Okay, you can also have a look at this problem, again very physical, right? That you have electric motor exerting 500 Newton meter, right? Okay, while we are doing this problem, you can always go through these pages. I will also try to post these pages for our online students. Anyways, you will find them, these problems that I'm making today, very easy. Okay. Okay, everyone, welcome to another session of 206. I hope you are doing fantastic. Great. So why don't you do this problem quickly? We have to scale up very fast. This is more like a repetition. The first problem is on the left side of the whiteboard. The second one is on the right side. The left side of the whiteboard is a separate problem. It says you have a shaft of length or circular rod for that matter, 54 inches. The torque is 250 foot-pound. One page for all of you. One page. From here and one page from there. Oh, okay. G is given to me in kilo-pound per square inches. The question says that you have to find the angle of twist. Quickly, calculator, do it. I need you to give me the answer in degrees. The problem is that, at least for the British system, it's very hard for you to have a physical idea because the torque is in foot-pound. But on the right side of the problem will give you a physical understanding, so don't worry. Okay, so I will do in parallel with you. I have TL over GJ. So T is 250. Okay.
Is that two problems or just one?
Two separate problems. Two separate problems. 250 foot-pound, one page for you from here and one page from you from there. Okay. And we have length is 54 inches. And then I have dia in inches. Dia in inches, TL. Let's convert this fellow into yes, good. So I will multiply this with 12 inch per feet and divided by, just so that students don't get confused. Okay, I'm multiplying this. Okay, divided by G is 11.5. My handwriting is not coming out to be smooth today. What happened? Okay. Then I have multiplied by 1000 kilopound per square inch. Multiply by J. Pi by 2. Pi by 2 d power 4. I always forget this. R power 4. Okay. The one formula that I always forget. I don't know why. Okay. Pi by 2 R power 4 is the formula as our students told me. Huh? I want the degrees. No. 28 is too big of a quantity. Yeah. 0.0283 radians. Huh. Oh, sorry. I think I multiplied. Sorry. Yeah, he's right. It is 54 inches. Oh, yes. Oh, okay, I did a control Z. Can I do a control Y now? No, I cannot. Oh, yeah, the torque is in. No. This is in feet pound. So I'm converting this feet into inches by doing a 12 inch per feet. Okay, the diameter is in inches as well. Yeah, so everything, I'm converting everything into inches. This thing is in inches. I converted this into inches by multiplying here. This is already in kilo pound per square inches. This is already in inches. Inches, everything in inches. Okay. Okay. Then I have phi in 0.0283 radians. Okay. And in degrees, it will be. What is the formula? What is the formula for radians to degrees? 180 over pi. Radians to degrees is 180 over pi. Very good. 180 over pi. Very nice. 1.6 degrees, correct? Yes, couple of pages for him as well. So you see a very physical idea, but unfortunately it is in feet pound. So let's do the right problem for you to have a better idea, because most of us, including me, we are comfortable in SI. So give me this one. Now for design purposes, you also want a rather limited twisting, right? So if I am allowing, let me make a line, because one of the students also got suggested that these are different problems. Okay. So if the phi max is given to me as 2 degree, give me the maximum torque. It is a hollow shaft, please remember. So C1 power 4 minus C2 power 4. C, I think we decided as the radius. Give me the value of J. I'm definitely not doing it. Okay, you do the whole problem. Okay, do the problem. Start the problem here. Start this. You can actually make a arrow like this if you want for clockwise torque or anti-clockwise, doesn't matter. Huh? So I will start the problem. Yes. Did I give you length? No? Okay, sorry. It is 1.5 meter. Thank you. You cannot start the problem if you don't have length. So I will do a phi max equal to 2 degrees multiplied by pi by 180 radians equal to TL over GJ. Okay. So I will have a nice and beautiful pi by 180 rad radians into GJ over L is equal to T max. Okay, give me the value. You already got it? Give me with the units. 1830 Newton meter. Good. Very good. One of the students told us it is 1830 Newton meter. Give me the value of J as well. Because I have to, at least in my notes here, I have to write it. Okay, no, I have to. So, end to end, the shaft or rod is allowed to twist no more than 2 degrees, right? Now I have the formula that phi is equal to TL over GJ. TL over GJ, right? So the maximum end to end twist is 2 degrees. I have to convert that into radians. So I get a pi by 180. So now that is given to me. Since it is max, with the TL over GJ, I also wrote T max. That's the maximum torque that will produce the maximum twist. Then I took all the other quantities on the other side. So I'm left with T max on one side, the rest of the chunk on the other side. And now I'm doing number 10. Okay. Okay, give me the value of J. That is 1.02. Seems correct. Thank you. 1.021 into 10 power minus 6 meter power 4. Should we proceed? Okay. You can also give me the subsequent shear stress, subsequent maximum shear stress. So I will get, what was the formula by the way? TR over IP. Instead of rho, I will put the, I will put 60 because it will exhibit 60 millimeter, the maximum shear stress. So I will put T max, which you found as 1830 here, into 60? 30. Thank you. Over, what was the J that you found? 1.021 into 10 power minus 6 meter power 4. 1830 Newton meter. 30 over 1000 meter. Boom. I don't know the value. You can give me the value. You can give me the value. Sorry, say that again. The value? What was the value, tau max? 15? 53.8 megapascal. You can double check, by the way, I don't have this in my notes. So. Okay. The maximum shear stress that he gave me. Okay, everyone. And maximum shear stress here TR over IP, it is 4.53 kilo pound per square inch. If you cannot find it, you can let me know. Okay, life is good. Is there any student who has any questions? Yes, no, no. You can take a picture quickly. The two students who just arrived. You can take a picture so I can go to the next slide. No, yes. Okay. Okay. 10, 7, 4, 2, 1. Okay. Boom. Let's quickly move to our the same continuity. Again, you are doing the problem. So assume this as pulleys if you want to. Okay. I have to come up with some nice drawings, by the way. And in the meanwhile, why don't you have a look at those 2 pages? There is a couple of concept applications. Why don't you have a quick look? Just so that I know that you are actually following. Okay. Because I need to be very good in sketching on whiteboard, which I am actually. So come on. You did see the midterm exam dates on CET, right?
Yeah.
Okay, good. Life is good. Okay, the question says, so you can assume this as pulleys, right? You have pulleys 1, 2, 3 on it, or I could have made nice and beautiful teeth, and you could have considered these 3 fellows as the gears. Of course, at the end of the day, you have power that is given to this shaft, which is transmitted, right? So right now for this problem, given to me that I have 400 Newton meter. And please remember that in most of these problems, we are considering one continuous shaft. The dia of those shafts can change, okay? But all of these, because just imagine if I have from A to C, and I have gear here, 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 and somebody is telling me that give me the twist, angle of twist end to end. Of course, this is one piece of shaft. Change in dia is happening, no problem, but one piece, right? That's why I'm talking about the twisting end to end. If there were separate chunks of the shaft, completely different, completely separate, why would I care about what is the angle of twist end to end? Yeah, are you getting my point? No. So one nice and beautiful continuous piece of shaft, dia is changing, can't care less right now. Oh, we do care, by the way. 800 Newton meter here. Then I have the torque in this direction. Then I have torque in this direction. Then I have this fellow in this direction. The question says that if the dia of this fellow is 30 millimeter and the dia of this fellow is 40 millimeter, are you getting my point? Dias are different, but it's one continuous chunk. If this fellow is my A and this fellow is my B and this fellow is my C, why don't you tell me 39 gigapascals? Why you guys don't give me angle of twist between, okay, I'm not writing the English. I think you get my point. Give me the angle of twist between A and B. Give me the angle of twist between A and C. Very nice. Thank you. Do it quickly. And trust me, they are seeming to be easy problems. They are not. The lengths are 1.2 meter. (1.2 meter), and the next one is 1.8 meter. 1.2 Okay, I need to change the color. It's not visible, right? Barely. 1.2. And this fellow is 1.8. Yes, no? $1,200, $800. Okay, hang on. Important piece of information. This is solid, okay? The whole piece is solid. Solid shaft. Okay, just again, this is a very basic thing. You wouldn't have even noticed it. When you talk about shear stress, right? You do that T R over IP, right? Right. What is that torque? Of course, reaction. Stress is reaction, right? But in this angle of twist formula, phi equal to TL over GJ, the T that you're talking about, that is the applied torque, right? I won't have a reaction. Like if I am twisting, the torque that I'm applying, that shows up in the formula, not some fictitious reaction. Are you getting my point? Something very minor, by the way, you wouldn't have even noticed, but anyways. Okay, you're not doing it. Tell me. Just start the problem for me. No, are they? Is the same problem? Oh, that's bizarre. I already gave you the solution for it. That's not good. Well, that was just
what you mean? It's not because it is really good.
yeah, that's good. It was, I just landed actually. Okay. So that's good then. I think we have solutions then. But you don't look at the solution. Do it yourself. Oh, really? Okay, that's fine. Then let me try this problem. How would I start? So always start in a very methodical way. You make a cut here, and then go like this fellow, right? I have anti-clockwise here, so the reaction. If I look from there, clockwise. So clockwise. So this is clockwise. If I am, oh come on, if I am looking from that side, that's clockwise. So I will have anti-clockwise. So I have TAB equal to 400 Newton meter, right? Clockwise. So this will be anti-clockwise, 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 looking from there. Okay. Then I have, I know you will find it unnecessary. The problem is so easy, but let me just go through the drill, because trust me, the problem gets complicated. You won't be able to handle it just by intuitions. So the next chunk is again, I will have, let's say again like this. You have one chunk here, you have another chunk here. So it is TBC, right? Let's write anti-clockwise. So that is clockwise minus 400. Then you have plus 1200. So I have equal to 0. TBC is equal to minus 800. So this means actually this fellow is clockwise, and I'm looking from there, right? Okay. Yeah, I know. I know I have made it too complicated, but anyways, So now phi AB equal to, you won't be using these signs now. I told you reactions, you can't care less. You will go for the applied thing. So it is T. And now you can ask me, then why are you even bothering to write it? TAB, LAB over GAB, JAB. So now I have this is, I will not use the anti-clockwise because when I'm looking from there, it's still clockwise. So I will use 400. I told you I will not use anti-clockwise. I am talking about the applied. Looking from there, the applied is clockwise. And it is 1.2 meter. This is Newton meter. G value is 39 into 10 power 9. Give me the value of J. This is one thing I actually need from you. Yeah, no, you don't have the value. Okay, okay, fine.
7.95.
Okay, you will give me the final answer then. Pi by 2 into what was the value of R? 15 by 1000 power 4, correct? 0.15 48 radians. Okay. Now you have to be careful. If you don't make a note here, everything is going crazy. You have to mention here that when I'm looking from there, 400 Newton meter is a clockwise. That's the applied torque. The twisting is happening in the clockwise. So you can see that I am not even bothering to use all of this because this fellow I wrote anti-clockwise because that is reaction. Okay, then I have the last chunk as, hang on, phi BC equal to, okay, do the whole drill for me. You have to find the J again, by the way. So it will be, this is TAB. So you can write here, not TA, TAB actually. But anyways, TAB will still come out with it. Okay, this one is TBC. I'm using prime here because I will not be using the same sign. Then LBC over GJBC. Instead of this, I will not write these symbols. I will just use nice and beautiful 800. And I will use here 400. Sorry, good, thank you. I was like 1.8. No idea, you have to calculate. But here I will probably, because clockwise I'm taking it, let's say positive. You can put a negative here if you want, but anyways, no need to even put signs here. So phi BC comes out to be 0.14. By the way, you also have the solution. You can double check with it. 0.14. 0.14. Okay. 0.1469. Thank you. Okay, hang on. Here, mistake will happen. You see, when you're looking from there, clockwise, anti-clockwise, right? It's opposite to this one. So this fellow was clockwise. This fellow is anti-clockwise. So if you don't write here, go by gone, it's a goner. The problem will be wrong. Students who don't like only this, they want to put a negative sign here, that's fine. Either way, at the end, you will have to do phi AB. Oh, we already found this, by the way. 0.1548 twisting in clockwise, and phi AC is phi AB plus phi BC, which is equal to, if clockwise is your, let's say, positive for now, it is going to be 0.1548 minus 0.1469. So you can always put a negative here. 0.1469, which is equal to, you can look at the notes, 0.0078 radians, which in degrees is, I don't know, you do it. So you got the point? Twisting is applied. Whatever reaction torque you are seeing, those signs are of reaction. Can't care less. It's a very applied thing.
In the transfers, say that for phi AV, it's not in clockwise direction, in anti-clockwise
Really?
direction. Yeah,
Really? That's not good.
for the direction of phi AV.
Show me that. What did you say?
It depends how we take the free body diagram.
Okay. Well, if we made a mistake, something to think about. It's your home task. What does it say? Oh, yeah. Oh, sorry. Okay. It's very good. He brought this up. Actually, the author is looking from here. I am looking from there. You see this arrow? You get my point? I have been looking from there, which is, I think, a little inconvenient. The author is looking from here, right? From here. So if you look from here, clockwise and anti-clockwise become different. So I'm saying that the twisting is happening in the clockwise when I'm looking from here. I think I need to make this announcement. Yeah, so his question was that the solution that you have provided for the author, it tells us that this is not clockwise, let's say this is anti-clockwise, and this is not clockwise, this is anti-clockwise, because the author is looking from here and I was looking from here. So that's why. Okay, I think everyone understood this problem pretty quickly.
I have a question about the direction of phi AV. We look towards right,
Like this.
like this.
I cut it. Cut it.
And we get the reaction like this towards this direction.
Yeah, so
So it will be negative in the reaction for the sorry. Yeah, the reaction will be negative. And in TA, which one of them we use?
yeah, for this one.
Yes, sir.
So for example, for me, the moment I cut from here, I know that the only thing that is appearing is 400 Newton meter, right? So actually, whatever you do, you have to just write a 400 here. The only thing you have to decide is what will be the reaction, I mean direction. So if you look from here, it's pretty clear that if you're twisting it, of course, this fellow will twist in anti-clockwise. But since I have been looking from there all the time, looking from there, it appears to me as clockwise. So I said, when I am looking from here, that's why I categorically mentioned this, that I'm looking from here. I know that the applied torque looks to me as clockwise. So I said twisting is happening in clockwise when you're looking from that direction. Yeah.
Okay.
And here, instead of TA, I substituted 400. I did not write T. You could have written TAB here, but that's fine. I think you get my point. Okay, why don't you do another problem? From the next time, I can start indeterminate problems. I know it appears to you that these are so easy problems, but trust me, these are not. Okay, I'm definitely not doing this. Why don't you do this problem yourself? Now, this time around, I have again pulleys or gears. Doesn't matter as long as there is something that is transmitting the torque. You are definitely doing this piece, I'm telling you. And the next one is another. Then I have a big motor, nice and beautiful. I hope I haven't brought the solution for this one as well. Really, I did. I don't know why did I print them. There was some reason. Now that I have given you, I'm thinking there was some logic behind me printing them. Not good.
Hocam, don't say it's not good. It is always good. Yeah.
Really? Well, from next time, then I can provide you solutions like this. If it's good for learning, That's fantastic. I have no issues. Okay, gentlemen, ladies and gentlemen, let's. Oh, I just. Okay, I think I messed up. Okay, let me quickly write this. Let me bear with me, please. You know how complicated drawing is. Okay, again, we have nice and beautiful shaft. One single piece. This chunk is 44. This chunk is 48. Yeah, I think I did provide you the solution. So you don't look at that, solve it. This is 1 meter, this is 1.2 meter, and this is 0.9, correct? 1, 1.2, this is 0.9. How many agree? Done. The question says that if the torques are, motor provides 500 Newton meter of torque, and this fellow is in this direction, that is 200 Newton meter, and this is in this direction 300 Newton meter. Then what will be the direction of this torque, by the way? Why don't you tell me? Here it will be, right? Because it is providing the torque, for sure, opposite. The question says that if G is 27 gigapascals, by the way, what is the name of G?
Modulus of rigidity.
Modulus of G is modulus of rigidity. E is modulus of elasticity. Okay. But of course, I know it, but I thought it is important that everyone remembers this. Okay. Give me the phi AB. Where is A? Please don't look at the solution. You do it yourself. This is A. This is B. This is C. This chunk is my D. Okay, A, B, C, D. Phi AB, phi BC, phi AB. What happened? Phi BC, angle of twist, phi CD. Done. Did I miss anything? 40, 44, 48. The same shaft, but its dia is changing. No, give your best shot. Give your best shot to start the problem. Start the problem. Perform the initial 2-3 steps. One single piece of shaft, but the dia are changing. 48 what? Oh, yeah. Yeah, thank you. That's 44 millimeter. Of course. 44 millimeter is his question, yes. This is 40, by the way. Did I tell you? This is 40 millimeter. Okay, you know what? I'm just finishing up a problem. So it is nothing. What is phi AB? Give me the value. 0, right? Why? Because there's no torque. Because if I cut it, so you have to understand one thing. There is a very smooth bearing here, right? There is a very nice and beautiful smooth bearing. So there is no applied torque. There is nothing, no torque here. Nice and beautiful bearing. Phi AB is equal to TAB LAB over GJ. And one of the students has told us this is 0. Boom, 0. No twisting happening in this chunk. Then phi BC equal to TBC LBC over G is the same for the, because it's one beautiful nice shaft, JBC. In order to find the TBC, again, you can make a nice and beautiful cut. So let's say I make a cut here, throw this chunk away. And yeah, so for example, if you, okay, you look from here, no confusion. So if I cut, throw this chunk away, I will put, let's say, reaction, let's say like this. So I will have TBC plus 200 Newton meter equal to 0, TBC equal to negative 200 Newton meter. And of course, I'm looking from here. This means it is clockwise, right? And in this way, give me the value of phi BC, please. 0.4?
No, 0.24.
0.024 radians. Okay, and of course, when you are writing this, I will not write clockwise, I will write anti-clockwise, because you can have a look from here. What is the applied torque? Anti-clockwise. So twisting will happen anti-clockwise, of course. It is an applied thing. Similarly, you will give me nice and beautiful, oh come on, where is it? Phi CD. Okay, so of course, I think all of the students agree that we should just cut from here, right? Instead of, and leave this. But I will go the hard way. I will start from here. So I have TCD, hang on. TCD again anti-clockwise. So I have, looking from this side, plus 200 Newton meter anti-clockwise, plus 300 Newton meter anti-clockwise, equal to, I'm cutting from here and leaving this away, equal to 0, and I have TCD equal to negative 500 Newton meter, which means that it is clockwise. But when I am talking about the phi, of course it will be anti-clockwise. Nothing fancy here. If you're seeing from here, you are seeing two chunks anti-clockwise. So it will be TCD over LCD over GJ. And the answer is 0.2, right? Anti-clockwise. And I'm telling you, just last 2 times I haven't done the calculation. You do it on calculator. There's a huge possibility of you guys making mistake. All of us making mistake for that matter. Okay. Our online students are not asking any questions. Why is that? Ehsan, Hasongkem, Uze. Everything is fine. Easy, right? Okay. Next time we will do indeterminate problem. Okay. Okay then. Have you have a look at this page then, front and back, everyone? Okay, for our online students, I can show you from the book. Everyone, is it clear? the power is equal to torque multiplied by omega, the RPM. Sure. Okay, take 5 minutes, go over the 3.6 and 3.7, ask me questions. For our online students, I can open the book. So 11:20, we still have 8 minutes today. Wow. I think we are done for the day. I don't know. So, let me share the screen. Okay, where is page number is 190?
187.
187, okay. 187. Okay. Hassan, can you confirm if you Hassan, Uze and Hasong? Can you see this? Yeah, this
Yes,
one. Okay. So, okay. So once you are done having a look at this, then I will go to the next one. Yeah, from here. Just go from here. And no, I did not. No. Of course. No, sorry. No. The reaction is of course opposite. So for example, let's say focus on DC and DC. And I'm looking from there. So it's going to be like this. Is this problem this one or the last one? Oh, I was. I think I made an error in this direction that we are looking from as I remember the focus on the left side. So this side. Yeah. Okay. So here, so we will show the okay, no, I don't get the problem. It's very easy. This on this side. Yes. I will ask you some questions. How the twisting will happen, let's say between these. How this twisting anti-clockwise, right? So the twisting will happen anti-clockwise. Yes, similarly, effect from here. How will the twisting happen? If both of these torques are anti-clockwise, for sure. There is one of them. Then you will have to make a decision which is larger, which is smaller. So for example, the clockwise is larger, then the overall twisting is larger. There's kind of logic. Simple logic. Look, the whole twisting thing is about applied torque. The shear stress is about reaction torque, because stress is more like a reaction thing. I am putting a torque like this. How the shaft is behaving in terms of shear stress, that depends on the reaction torque. But the twisting is applied torque. So it's just you look from one side in an exam setting. Make a decision, keep on making cuts, but keep on looking at it.
So find we are looking at the applied torque.
Absolutely.
Yes, okay.
The only reason I am making these cuts and showing you the reactions, these talks, is because I'm doing more and more practice, so you understand that this is more like a revision of statics from my side. Okay, done. Okay, what about online students? You had a look, right? Okay, should I go to the next slide? Our online students. Okay, boom. Okay, so now you have an idea. It's a very practical problem. There is a motor, there is a power that the motor is giving. That power is in 100 kilowatt. In this problem, the shaft is rotating at a frequency of 20 cycles per second. You see, you have that page with you, right? Our last students. Okay, good, because it's not clear here. So you convert that into, I don't know, radians per second if you want. So you find the torque that is transferred, and in a methodical way you arrive at the answer. You have that page with you, right?
Yeah.
This one.
Maybe this is the piece.
Okay, this one. So we find torque, then we arrive at this. Okay, I think it's clear.
There is something that stuck in my mind.
Yes.
In this problem, and also in the other problem,
Huh.
3.6 and 3.7,
Uh-huh.
the frequency of the shaft is a fixed number. So it means it's rotating with a constant angular speed.
Oh yeah,
So
because the object is in equilibrium. Of course, if the object is not in equilibrium,
if there is not an acceleration,
because
also it's supposed to be have a torque also, because there is not an acceleration.
oh, well, look at from this perspective. You have an applied torque. The one thing that should be clear. I understand your question, and there's an answer. If you look at that page, the other one, that page has the answer to your question. You see, the question says electric motor exhibits or exerts a 500 Newton meter torque. This provides 500.
Yeah, but the thing is accelerating because there is another
300 and 200. If it had provided, then that would mean that the load is 300, 200. Then the RPM would be in yeah, exactly, transmit mode, and we would have to wait. It will keep on increasing because your load is 200 and 300 and you're putting a value. So in all of these problems, in all of them, 400, 800, so these are all equilibrium problems. We actually are not looking at that. I switched on the motor and the shaft is now arriving at a steady state. I'm not observing those. I'm talking about a steady state system. If you switch on, switch off, switch on, switch off, switch on, switch off, that's more like a cyclic periodic stresses that you are subjecting an object to. That's more like a design of machinery concept. We are at a very basic phase that the object is in equilibrium at a constant RPM because the torque provided by the motor is equal to the Okay. You had those pages, right? Good. And you understood. And everything is clear, right? Sure. Well, thank you. Let's see you in the dynamics if you're taking that course. What about Hassan and Hasung? Everything is fine? Okay. Thank you. Okay. Thank you. Bye-bye. PNG, PDF.